Okay, guys, if you haven't sent me your attendance text, go ahead and do that. Going once, going twice, and it's gone. Okay, couple things before we start. So in the last class, I asked a question about possibly continuing the remote delivery of the lecture, and I had 20 people that said yes, either they're okay with it or they don't mind either way. So I just recorded that as 20 yeses. I had 2 people that say no, and I had 3 no responses. And then of the 2 people that said no, I asked if you wouldn't mind if you would send me a text so we can talk. I just kind of wanted to drill down and see kind of what your thinking was and maybe why you would not want to continue remote for a couple more weeks. And one person actually had a good reason. Only one of the 2 people contacted me, and we talked by text, and they said they learn better face to face. And I actually agree with that 100%. I get that because I'm the same way. I think if I had to some of the classes that I've done in the past, some of the classes that you guys are doing now, if I had to do like a physics or thermodynamics remotely, I don't think I would absorb that material very well. So I feel you, I understand that 100%. But that person also said that they kind of understand my situation, and they said they'd be willing to go and do the remote for a little while longer. So I want to tell you, I'm not going to mention the name, but I do appreciate that and thinking about my situation. The other person never contacted me, so I'm not really sure. But just kind of give you an update of where I am with that. I contacted the department because I decided what I'm going to do is just try to push this thing and stay remote. I don't know, at least until the numbers drop or maybe the weather breaks or something like that. I got a email back, and they said that they need to look into this. This was Friday. So I think we talked on Friday. I emailed the department on Friday. They did respond rather quickly, but they said they need to look into it to see what needs to take place in order for me to continue to do this thing remote. So I guess where I am now with it, I'm going to do Wednesday's class by remote. I'm hoping to hear from the department either today or tomorrow. If not, I'll send them another email. For the one person that did say that it is a little harder to learn through this video thing. One thing I think that's okay about what we're doing right now is that for the next couple of weeks it's just PowerPoints, and so I don't really think. I think if I had to deliver a lecture, I would rather it be PowerPoints than any kind of calculation or anything else that I might have to do on the board, any kind of board work. PowerPoints, I think they lend themselves to what we're doing, so I don't think you'll have any issue with it at all. So they could come back and say, no, you have to go face to face. I don't know how they're going to respond, but the issue is, I think if I get sick, and I didn't mention this in the last class, but my sister, she tested positive for COVID 2 days before I made the announcement to you guys about continuing to go face to face. So I am vaccinated, but if I get sick, I just don't know who would take care of my mom. So I'm really, really uncomfortable with going back, at least right now. So where I am right now, I'm going to wait to see how the department responds. Hopefully they'll respond today or tomorrow. If they say no, then I guess I don't know, I'll just have to bite the bullet. If they say yes, we'll continue to do this for a few more weeks into February, and then we'll switch over to the format to where we'll meet. I'll just keep you guys updated. But I mentioned in the last class that this will be delivered via today's lecture, the web, and then Wednesday we will be face to face. I'm going to wait and hold out and see what the department says and just continue this format. I will, because I don't know what you guys are doing before this. I don't know, if it's an issue setting up a computer to get a spot to join the class. So I know we start at 9:05. I'll wait a few minutes for each lecture just to give you guys a chance to get situated while I do this. And then I'll keep you updated. And there'll be a permanent decision made this week. I'll promise you on which way we're going to go with this. And if we do continue the online, it won't be for the whole semester, just until the numbers are a little bit better. And I think this weather breaks. I think I'll feel a little bit more comfortable with meeting on campus. I teach 4 other classes, and none of my other classes are face-to-face. We're all remote. So just to put that out there. So that's one thing. Anybody have any comments or concerns about the statement I just made? Because I got a couple other points I want to cover too. Okay, if you do, you can text me privately or we can talk on the phone, and I'll be happy to still take your input and consider. But I think for the most part, you guys are in the support of doing that, and I really appreciate that. The other thing I want to remind you, in the last class, we kind of ran out of time as usual, but the control circuit, I showed you a basic control circuit, the one that I introduced to you in the beginning of the semester, the AND circuit, a 2-input AND, where on the left you have a power source, and I drew a DC power source. This is a battery. And then you have your inputs. I showed 2 inputs, but for AND logic, you can have as many, you got to have at least 2, but you can have as many inputs as you want. So these are my inputs, A and B. And then there is your load. That's whatever you're controlling. I always draw a light bulb, but of course in this class, it'll be a motor starter, a conveyor. There'll be some industrial device you'll control. And what I mentioned is really what we're going to do is we're going to draw this a different way. Instead of drawing the actual circuits like you learned in your DC circuit analysis course, I want you to imagine 2 wires. Here's a wire, and here's a wire. And typically in electrical engineering diagram schematics, they draw input, power sources on the left and loads on the right. Typically they do. Well, here in this, what we're going to do is just we're going to take this battery and we're going to put it up here like this. And so now I basically electrified this whole wire and this whole wire. We're going to call this line 1 and line 2. And then what I'm going to do is just draw my switches in between these 2 wires. It's really the same circuit, just kind of drawn a different way. So I'm going to take my first switch and connect it to this wire. Second switch, that wire. And then the thing that I'm controlling, the load, the output, is always the last thing on the rung. So my light bulb would be here. And so we understand that the power source is here, but we never draw it. We'll take that out. We'll just imagine that to be there. And speaking of power sources, what I mentioned is I just erased the battery, that's DC, but you can also have AC power. So you might see a source like that, that's AC. And typically this will be 120 volts AC or 240 volts AC. If it's DC, typically I think 24 volts DC are standards. But anyway, basically these are the two. These are 2 exactly the same circuits, but this is called a ladder because it looks like a ladder. And you know, I can keep putting. I mentioned in the last class that if you have a ladder and you got the rungs of the ladder. Well, these are like the rungs of the ladder. So they call this a ladder diagram. And they use this in control circuits. So this is the way. I probably will never do this in this class again. This is the way we'll think about it. Just kind of want you to see that. And I can add another rung in here if I wanted to. I can add, maybe I got another input. And now somebody asked a good question in the last class. You might have missed it. At the end of the last class, they said, can you connect 2 rungs together? So let's say I have this switch. This is switch A, this is switch B, this is switch C. You can do this. I can take a wire and I can go to like this rung right there, but that really is just the OR circuit. When we talked about the OR is just things in parallel. You cannot do this. You can't have a rung down. Let's say I have a rung here and a rung here and then some other output right there. This is switch D. You don't want to do that. You don't want to connect them together like that. But it's okay to OR things. So if I have something coming out like that, that's really not 2 rungs connected together, because the definition of a rung is going to have inputs, which are switches or buttons, and it's going to have an output. So if I had another output down here, I had some other device, maybe another lamp, and then you did that, then you're actually changing the circuit, and that's not what you want to do. So the answer, I think I told that person that a rung is a complete thing. So you can't take and connect two rungs together, but don't confuse the or. If I come off of the bottom here and or these two switches together, don't confuse that with connecting two rungs together. That actually was a good question. Whoever asked that, that was a really good question. So let's see. And the other thing, somebody asked if I would activate the past video. So I put everything we've done so far is up on your Canvas. There's a link at the bottom of your home page. It says past videos. Hit that, and then put all the actually put the videos there instead of the links. Last time I think I put the links. So those are there. And then there was one more student that asked about today's video. They have an emergency appointment, I think a medical appointment, and they wanted to know if I could put this video up right away. So I'll do that. I think this system I'm using takes a while once we're done, it takes an hour or two to render the video. But as soon as it's uploadable, I'll get that up, and I'll just send a link out to the class to let you know that today's video is available. And let's see, ladder thing. I think that's all I wanted to cover before we get started. Anybody else have any comments or concerns before we start? Okay, if you do, I'll stick around after class. Let's jump into this. This is getting to the good stuff. Then we'll get to some programming. I think you guys will enjoy that. So in the last class, one other thing. I know what I forgot. Remember I told you about printing out the PowerPoints. This is what I was saying. If you zoom in on this, if you print out the PowerPoints like this, then I can talk about whatever is on the slide, and then sometimes I'll say this is on the exam, this is on the quiz, or sometimes I'll say you need to remember this, or just I might have some commentary on this particular slide. And if you do it this way, you can write it over here. And then if you 3-hole punch this, like I asked you to get a 3-ring binder for the class, you can put that in your binder, and you'll have a really, really nice packet that you can use to study for the course. So when I mentioned note pages, this is what I was saying. You can print this out in your PowerPoint, your Microsoft PowerPoint in this form, and that lends itself really, really good for the class. Now in the last class, I introduced the actual PLC to you. If we were face-to-face, I would have actually brought in, I have an old PLC that I keep just to bring in and kind of do the show and tell. So I showed you the actual, a typical PLC, and we talked about some of the parts that are named here. Today we're going to get into, well, this controller right here has the most important part, the CPU, the central processing unit. So we'll talk about that. We'll talk about the I/O system. This thing right here, that these are modules. These things you can pull out. These cards, you can pull those out, and you can move them around. And the thing that they sit in, the actual chassis, is called a rack. So we'll talk about some of the physical parts of it. And so what we were doing in the last class, if we just kind of recap, was kind of an overview of this, programmable logic controllers. And I asked you to remember a couple things. One is that a PLC is very much like a computer. Matter of fact, they're pretty much the same thing. A PLC, your cell phone, any digital device are all computers. Computers are going to have some basic parts that we talked about. We'll cover again in some of these PowerPoints. But we also mentioned that a PLC is a solid state device. Well, not just a PLC. Well, any digital device is solid state. And basically for now, on this level, all that means is that there's no moving electrical parts. Everything is done on a silicon crystal. Solid state means no moving parts. That's an advantage, because if there's no moving parts, there's really nothing to wear out. And there's other advantages that we'll talk about. So we talked about that. We talked about some of the things that PLCs can perform. Mainly in the old days, control circuits were put together using relays and switches. So PLC can mimic a relay. It can mimic switches. It can actually switch actual relays and be controlled by actual switches. It can count, calculate, compare. And somebody asked a good question. at the end of the last class. It says, okay, what does it mean? Analog processing, analog signal processing. So I don't know if I explained that in the video or not, but basically, you know, there's going to be two types of inputs. The main type of input we deal with, I shouldn't say the main, the most common is discrete input, where you have a switch or button that's in one state or another. It's open or closed. That is the discrete, what we call discrete I/O. But sometimes you want something to happen. We live in an analog world. When some analog quantity reaches a certain value, and so if I want to feed that to the PLC, if I want to feed that to the computer, I can't take an analog signal and put it directly into a digital device. I got to do stuff to it, and that's the processing we refer to. We kind of already touched on that the first week of class when I showed you the analog signal and how you would sample that signal, and then each little dot, each little sample, you would give that a binary code, and then you would store that code. That's the process of digitizing. We talked about the digital advantage. That's kind of what this bullet point here is alluding to, but it's a little bit more than that. And then we talked about the fact that a PLC is an event-driven device, meaning like unlike a computer where you can hit go on the computer, it's going to run through the software. The thing that makes a PLC program advance from one, let's say line for right now, but we mean rung, from one line of code to another, or from rung to another, is something has to happen in the field. The field being all the hardware, the factory, the switches, the sensors outside of the PLC. A switch has to open or close. A button has to be pushed. Something has to happen that PLC will respond to it, and then depending on how you wrote the program, it'll react to that and then move to the next rung. So it'll sit there. If nothing happens in the field, it's just going to sit there like your car idling. It's not going to do anything. So it's an event-driven device, and this is a good way to think about it. And we'll come back to that, and I think you'll understand more of what I mean by that as we get deeper into the course. You want to mark this slide. I don't know if I said that in the last lecture. You want to know the main parts of a PLC. Actually, guys, this is the main part of anything that we call a computer. And remember, in this class, a computer is anything that contains a microprocessor. Any computer is going to have these parts, but specifically, a PLC is going to have a CPU, I/O section, power supply, and a programming device. And in that picture of the PLC I showed you at the beginning of class today, you saw everything except for the programming device. And there was an extra module there called communication module. We'll talk about that. So mark this slide and know that. And then I think we kind of breezed over this one. Here's some input and output devices. These different. You'll be familiar with these throughout the course. I'm not really too much worried about this slide. There are various switches and buttons. We talked about the difference between the switch and the button. Well, there are actually different types of switches, and there's different ways we draw them, different schematic representations or graphical representations we use for certain switches or types of switches. And when you get into your simulation software and we get deeper into the class, you'll start to just kind of pick up on that by just seeing me use them and seeing them on the problems and all of that. So just kind of go over this. You don't have to memorize anything here, but it's good to know about that. Now, I kind of went through this one kind of quickly. I want to back up. In the world of PLCs, there are what we call physical devices or hardware, but a lot of things that we use in control circuits and hardware can be mimicked in the PLC in software. And that's always a good thing because number one, it's less expensive, and number two, you can have as many of those things as you want if it's software. So the main thing, the number one thing of a PLC is going to be the relay. And so you guys, I think we talked about how relays worked on the board. You watched the video where the guy, Jeremy in the video, talked about, showed you how a relay works, and you've seen symbols and since we've been talking. Basically a relay, if we think of a relay with one pole, one switch in it, that relay can be opened or closed. A relay can be opened or closed. So a PLC can either mimic a relay contact, those are going to be our inputs, or it can mimic a relay coil. And often relay coils in the PLC circuit is the output. It's what controls the output. Sometimes you have a big device that you want to connect up to a PLC. When I say big device, I mean it draws a lot of current. So you can't take, say, a motor. Maybe you have a 10-amp motor. You couldn't take a 10-amp motor and connect it directly to a PLC. If you have to interface it, and the way you would do it is use a relay. Remember, a relay uses a small current to switch a large current. I gave an example of your car starter back a few weeks ago, so that you understand that. So you can use the relay to interface with some other kind of heavy equipment. But really, when we think about it in a control circuit, we really just kind of look at the coil. We don't look at what is controlling. And so, number one here, you can have a virtual relay. And since a coil is either on or off, we can represent something being on by recording a logic state of a true or one. We can mimic a relay being off by recording a logic state of false or represent that with a binary 0. And you'll see how that works as we progress, probably today as we progress in the course. So mark this slide, because I think at some point I'll ask on a quiz or exam. I don't know if I asked you to name virtual devices or just mark this slide on your PowerPoint or take a picture of it or something. And remember, you want to know what a virtual device is. A virtual device is a software device that mimics something in hardware. And then there's these three main virtual devices. We work with PLCs. Are going to be relays, timers, and counters. The simplest thing to represent inside of a relay, inside of a PLC and software, the simplest thing is going to be a relay, because a relay contact is either has power or no power. Anything that can be in one state or another can be represented with one single bit inside the PLC. If it's more complicated, like a timer or counter, then that's a different story. You can't represent a timer. A timer is a complicated mechanical or electrical device. So you can't represent that with one bit in the PLC. Same with a counter or timer, either one of those. So it can be done, but it's a little bit more complicated. And by complicated, really all I mean is it takes a little bit more of those zeros and ones, takes a few more of those to represent the information that you would need to model a timer or counter inside of the memory inside of the PLC. So we'll come back to that. We'll dig into that. But what I actually wanted to get to when I ran out of time was this, because here is where we actually start to understand. Okay, I get the parts, I get the digital stuff we talked about last week, I get the analog stuff, but how does this all come together? Now, I drew this slide, and I'm no artist, so I tried to do my best. This was back in 2004, and so I tried to draw this process here. So take a second and just read this over on the left. Read this. There's a couple important things I want to point out here when you read this. So first thing is understand the process. You got this big tank. You got a fill valve over here. You got some liquid coming through the fill valve, filling the tank up. You got a motor here. And if you read the narrative over here, it says mixer is used to automatically stir the liquid when the temperature and pressure switch reach preset values. Couple things here. Anytime you're reading, anytime you're reading a problem and you see the word and, you see the word or you see the word not, you probably want to highlight that. That's important because that's giving you information. Really, it's kind of telling you how to connect those switches. It's a little bit more involved in this, but this is a really simple example. So on this PowerPoint, I have the and word highlighted. So you can kind of imagine before we go to the next slide how we're going to have to design the control circuit. If I want the it says mixer is to be stirred when the liquid and it's the temperature and the pressure. So the switches, there's some switches here. There's a switch that will either open or close when the pressure reaches a certain value. They call the preset value. And there's a switch over here when the temperature reaches a certain preset value that you set. And when it reaches those preset values, the switch is going to change state. Now, the other important thing I want to pause and take, just kind of have you think about, look down here in the corner. This is important right here. It says, note, temperature and pressure switches close their respective contacts when conditions reach their preset values. They close their contacts. So let me ask you a question. Are those contacts normally open or normally closed? Anybody?
They would be normally open.
They're normally open. If they close their, now y'all would think about what the definition of normally open. We said if I take a button, if I take a relay, if there's a spring, either keeping the pole against the contact, in which case it's normally closed. If the spring is keeping the switch open, it's normally open. And then some actor, a person, a device, something has to close the contacts if it's normally open. So when we're doing what we're doing in this class, if you're actually wiring up, I don't know, your process, your process that you want to automate, you got to know what kind of switches you're dealing with. Doesn't matter, because if it's normally if it's normally closed, we got to use a certain instruction. If it's normally open, we just kind of got to know where our starting point is. Now I'll dig down into this deeper later, but make a note of that. You got to know the things I'm working with. They're normally open, normally closed. Usually, you guys, well, you could be doing anything when you graduate, but typically you'll have a plant electrician come in and install the switchers, buttons, sensors, and all that. You'll come in and you'll write the program, but you still got to know, hey, is this switch connected to this device? Is it normally open or normally closed? So we have normally open switch. In this case, the actor I'm talking about will be, well, one is temperature and the other actor is pressure. That's the thing. Those are the quantities, physical quantities, that will close a switch or allow a switch to open up. So if you got this in your mind, how would you wire this up using switches, the old school way? If you were going to use switches to implement this, how would you do it? And it's actually pretty simple. You're probably thinking, well, here's what I would do. I got an AND circuit because they said that I want the mixer to come on when the pressure and the temperature are, I'm going to use the word true. When the pressure is true, meaning that it's at that preset value that we set. And when the temperature is true, meaning it's at that preset value that we set, then we want the mixer to come on. But I want you to look at this ladder. Let's study this. Look closely at this ladder. So I mentioned earlier the line 1 and line 2. You can see these lines right here. Now this down here is not part of it. The ladder is just this. Here's my ladder. Forget the thing at the bottom. That's just showing you that my power source is not DC, it's AC. So there's my ladder. And the way you read the ladder is, we think of current, we always think of, for now, we'll think of current flowing from left to right. Anytime we read a ladder, a physical ladder, current always flows left to right. And the very last thing on your rung is always the thing you want to control, your output. Now ignore this right here. Ignore this. That's not your output. Your output is actually here. And that is a coil of a relay. Remember I said earlier that you don't want to connect heavy devices right to the output of the PLC. You'll use a relay, and we'll let the relay control the heavy current. So typically our outputs are going to be relay coils, and we'll just right now draw that as a little circle. So this says motor starter coil. A motor starter is just a heavy duty relay. And ignore this. Anytime you see that, that's an overload contact. We'll talk about that. I'll actually show you guys. Hold on a second. I have a motion detector in this room, and when I don't move, when the students are not here, so then it turns the lights out and you guys can't see. So anyway, what I was actually trying to get to is, you can see how this works. Pretty simple. When this is an AND circuit. It said when the pressure switch and the temperature switch reach their preset values. So if the pressure switch reached its preset value, then this will close. But still, there can be no current flow because the temperature switch hasn't reached its preset value. Once this switch is closed, I have current continuity. That's important. Current continuity. There's two kinds of continuities we're going to talk about in this class. Current continuity and logic continuity. Now this is a physical electrical circuit here. They work off current continuity, but when we actually get into the writing programs, that's logic continuity. We'll talk about the difference. Actually, the first lab you'll do, we'll explore that. But anyway, so we have continuity, which means I have a continuous path through which current can flow. Current is always going to flow from line 1 to line 2. So I have current. So now this thing is going to activate, and the motor is going to spin. It's going to mix up the liquid. Or instead, if I want that OR circuit, it said either the pressure switch and the temperature switch have to be true, or the manual push button. So I've OR'd this, or I've basically an OR is a parallel. So if I press this button here, now I have a pass that bypasses the and I can still operate that. Now, the problem with this is a really, really, really simple control circuit. I mean, really simple. But if you wanted to change something, let's say you wanted to change the logic so it's more like this. If the pressure switch or the manual switch is closed and the temperature switch is closed, that's a different circuit. But you have to get in there and physically rewire it. Well, that's where PLCs solve a big problem. So remember when I showed you the PLCs, we had those modules, we had those input modules and output modules that I referred to. Well, this is my attempt to draw an input module. And so you don't have to understand the details of it, but the basics of it I want you to understand. So here's my line 1 and line 2. So don't worry about how that's connected right now. That's not important. It's 120 volts across line 1 and line 2. Now, instead of doing this, instead of actually wiring this up like this, instead of doing that, if you're going to replace this control circuit, this hardwire control circuit, if you're going to replace this with a PLC, then what you would do is you wouldn't do any of this right here. You throw all this away. You get rid of this. And you get your PLC, and when you have your PLC, this input module right here, each one of these represents a screw terminal that you can connect the wire to, and the wire is connected to either a switch or a button in this case. And so we know we have 3 switches or buttons. We have a pressure switch, normally open. We have a temperature switch, normally open. And we have a manual push button, which is probably a normally open push button. And when you release it, it's going to open back up, just like the doorbell we talked about in the beginning of the semester. So what I'm going to do with those switches is I'm not going to connect them up like this. All I'm going to do is wire them directly to those screw terminals, PLC input module. And so if you just just look at that for a second. Now, there's a couple things to note here. First of all, this is wrong, because it's not a big deal, but when we number things, and this actually turns out to be pretty important, when we number things in digital, we start with 0. So technically, this number 1 should be a 0, but don't worry about that right now. Right now, we'll say, all right, this is the first terminal right here. This is the second terminal, third, and so forth. But this is very, very important. This is really important because this is the address of the first terminal. And this is the address of the second terminal. And this is how the PLC is going to know which switch is where. And I'll show you that in a second. What you're going to do, though, is, as I said before, you're not going to hardwire those switches together like that. We're not going to do that. What we're actually going to do is connect the switches to our input module. And then in software, here's the circuit we're going to build. Now, this is a weird kind of a language. If you guys, I was talking to somebody, and I forgot. When I was in school, I took Fortran, I took C, C++, a couple other languages, and I forgot what he told me, you guys. I was talking to somebody on the phone and said, you guys do your math thing, some other things. I don't know what you guys learned. This ladder logic, relay ladder logic, is a graphical language. So instead of using a high-level language that uses English terms, it uses symbols, graphical symbols that will be familiar to a plant electrician. These are electrical symbols. And so what you're looking at now is this is the actual software. This is what you would bring up on your computer screen, and this is what you would program. And notice, you'll recognize that the layout of this is very, very, very close to the layout of this. if you look at, we have an AND circuit. We got a pressure switch, we got a temperature switch. They're ANDed, meaning they're in series. Well, if you look at the program, you have this. This is a relay contact. We use a symbol for a relay contact as part of our instruction set for PLCs. So basically right now, this relay contact right here is going to represent a switch or a button, and this relay contact is going to represent a switch or a button. And this is going to represent a switch or a button. Well, look at this. If you go back to this diagram, remember when we connected the actual switch or button to the module? This address right here and this address right here correspond to the address that you would write in your program. So it knows that that pressure switch is here because you give this that address, and it knows that the temperature switch is here because you give these that address. And the fact that you put these in series, it knows that they're ANDed that. And it knows that that manual push button, because you've given it that address, you said, well, this button is at address 003. It knows where these things are from here. The beauty is, if you had to change this, you just delete, drop, and drag. This is all software. There's absolutely no wiring here. Now, I can't see your faces. You can see mine, but I'm telling you guys, this is big. This is huge when they came out with PLCs because, as I'll show you at some point in the next day or week or something, when we had these manually these hardwired control circuits, you can imagine if I had a plant like General Motors or Ford back before PLCs, and they had this logic control stuff. It was all relays and switches. And if you had to change something, back in those days, they would change the cars every 2 or 3 years. They changed the model year, which means some process had to change. You had to go in and rewire something. Well, anywhere between 85 and 95% of the circuitry in a plant like that was all logic. It wasn't the control. It was the control part. It wasn't what you were controlling. It was the logic part of the control. Now, I actually have a diagram. I want to show you that, but I don't know if we go face to face. I'm going to pass it out to you. If we don't go face to face, I'm going to just show it on the screen. So it depends. I'm going to wait. But the point is, this is really, really big. The fact that we can now take all of this and represent it in software, because the circuits you're going to have to represent are really way more complicated than this. If I want to make a change, it's as simple as drag and drop or deleting something. So this is like, I don't know, this is big. So I don't know. Let me go to the next slide. I'm getting excited over this. Let's see. So I guess just kind of read through this. I'm not going to read it to you. This is cycle. There are a couple important things here. Let's see. They talk about right here. So well, let's just go through it. So this will make sense. So you already know this part right here, that you enter the ladder into the PLC. But then the steps you go through is that you would actually take the programming device and you would enter the ladder into the programming device. It could be a handheld programming device. It can be a computer. Nowadays, most of the time it's a computer. So that this thing right here is your program. You would enter that into the computer. And then you have to move it from the computer to the PLC. The programming device, be it a computer or a handheld device, it has its own memory. And that program that you're putting together is in the memory of that programming device. You got to move it over to the PLC. So there's going to be some kind of button or something you press so you can transfer that file you're creating from the programming device to the PLC. At that point, once it's loaded, that's where it said here you're going to put the PLC in run mode. The other mode would have been called edit mode. And then here's what the PLC is doing. It's going to look at the inputs. It's going to run the program. It's going to change the outputs accordingly. Now, it's a little bit more involved in that, and I'll dig down into the details of that in the later PowerPoint. But basically, that's kind of what happens. But the thing I said I want you to remember, these are the two most important over here. We'll talk about what this is later. But it says the completion of one cycle, a cycle being this thing down here, bullet point 3. The completion of one cycle is called a scan. That's one scan. And the time it takes to do a scan, amazingly, is called the scan time. So that turns out to be kind of important. I don't want to go into the details of why, but you can kind of imagine that if the scan time is too slow, if I have a switch or device opening and closing faster than the scan time is happening, you can see where that might be an issue. Again, we'll come back to that. And then the last thing in this PowerPoint is, well, this is not. So there's basically, in the world of PLCs, you have programming tools. I think the main way PLCs are still programmed now is using relay ladder logic, but there's other ways you can do it. There's something called function chart programming. You can use high-level languages like C, C++. There's other ways to program PLCs, but the point of this slide is you have programming tools that creates your logic, your control logic, and then over here you have tools that you can use to monitor the industrial process once you get it up and running. So we'll talk about that the last week. That's human-machine interfacing, and so that is a whole different thing by itself. So we won't get too much into that, but we will look at a little bit of that. Now, I want to move to the next PowerPoint because I still have 10 minutes, but let me slow down and pause. Anybody have any questions on anything in the PowerPoint I just went over? Okay, well, let me go to our next PowerPoint, and let me see, which one do I want to do? Okay, do I have time to do this one? All right, let me show you something, guys, real quick. I'm going to try to do, no, let me just do the CPU. I'll do the CPU. That's probably easier. Do I have the CPU here? Oh, right here. I wanted to do the I/O section, but we'll do that next time. But let's do the CPU. This is probably easier. Okay, so now you know the major parts is the I/O section, input output. You know you have the CPU, central processing unit. You know there's a programming device. You know there's memory. You've seen those pictures a couple times, and I'll continue showing them as we go through the slides. You'll know these basic parts. Now we want to just kind of look at each section and go into some detail of the important sections of the PLC. So I think we got enough time to do this one. The CPU. So CPU, first of all, stands for Central Processing Unit. Anything that's programmable that we say has intelligence. I'm not talking about AI, but just anything we will refer to as a computer is going to have a CPU, a Central Processing Unit. And that Central Processing Unit has 3 main subunits. It's going to have the microprocessor. It's going to have memory. It's going to have a way to power the memory and the microprocessors. These are the 3 main parts of the CPU. Now, the computer science people here are not going to like this, but for purposes of this class, we're going to consider the microprocessor and the CPU to be the same thing, even though we know the CPU is bigger than that. The CPU actually contains the microprocessor. But just to make things easier to think about, later on when I say microprocessor, CPU, you can kind of use them to be the same device for right now. So that's the note at the bottom. So you probably want to remember the basic parts of this. On most PLCs, you'll have a way, and I mentioned this earlier, when you are actually creating the program, the PLC is in one mode, and when you download the program to the PLC, it's in another mode. And then there's other modes that you might have. The 2 main important modes are the run and the program. So when you're actually running or editing the program, you're going to have this switch here. And when you're running it, you're going to have it here. This remote, some PLCs have that remote, some don't. You'll get this in your simulation software because he actually does a pretty good job of mimicking a real PLC, be it an older one, but it mimics this pretty well. So you'll see that, you know, you got to have a switch in one position when you're editing and another position when you're actually running the program. And he does a good job with that. So the PLC, these point, executes the operating system. So what is an operating system? Well, you're kind of already familiar with operating systems because, I mean, you probably use Windows. You probably use a cell phone, and your cell phone, depending on if it's an Apple cell phone or the, I don't know the other name brands, but basically an operating system is software that separates the application from the hardware. Let me just go to the camera real fast, I guess. So in the world of computers, you have, this is you, this is the user, and then you're gonna have some app you use. This is an app you use. So this might be Microsoft Word, or it might be some app on your computer. Some teenagers were telling me about something, TikTok or something they were saying. Those are all apps. That's a piece of software. Well, that software, the lowest level down here is the actual hardware. So this is hardware. So hardware, I might have, well, you know, it's anything you can touch, hard drive, thumb drive, printer, that's all hardware. Well, that application, that Microsoft Word, that TikTok, that whatever your app is, doesn't interact with the hardware directly. There's another layer of software in here. And even though I'm drawing it as one layer, it's actually several layers, the operating system. So we're going to call this the OS. So basically, think of the operating system as it's a software, it's a set of software programs, but it's a program that basically interfaces the application software with the hardware. So on Microsoft, this was Microsoft Word. You know, you got the little thing up there, you can press print. Well, that print signal is interpreted by the OS, the operating system, and it gets the hardware to do what it needs to do to print. So I don't want to say any more than that because this isn't really a computer course, but any computer is going to have an OS. It's got to have that. Let's see, where was CPU? See if it comes back to where it was. Oh, all right. So we were on. Okay, so the OS and the manager's memory. We won't get into memory management. This is just some of the things that the CPU does. So I would say mark the slide and just kind of be aware of what it does. I'm not going to ask you to memorize this. Now there are some things I want you to memorize, but this isn't one of them. So I think it's important to know what we mean by operating system. You've heard of operating systems. You know that there's Windows operating system. You heard, but I don't know if you know actually what it does. So I just want to mention a little bit about that. So mark this slide. Now this next one tells us what memory is for. We want to know what memory is for. We want to know how it's laid out, and then we're going to talk about some terms, useful terms that you got to understand what's going on inside of any digital device. So memory is where the control plan or program is stored. Now, it's important to understand that there's memory and then there's storage. There's memory and there's storage. And so we're talking memory. The difference is memory is temporary, storage is long-term. Memory is only active when there's power. If you remove it from memory, then whatever was in the memory is gone. Whereas storage, so one example would be you're typing a Word document. You haven't saved it yet. Maybe you got a thumb drive plugged in the computer. You haven't saved it. You're just typing the Word document. Well, where does that Word document exist if you haven't saved it? Where is it? It's in memory called RAM, random access memory. And if you don't save it, if you unplug the computer and power goes away, when you plug it back in, your Word document is no longer there because memory is what we call volatile, which means that in order for it to store the contents, it's got to have power. Storage is non-volatile. It'll store it with power or not. So you want to actually store it, what you would do is you save it to your thumb drive. Now that's long-term storage. That's not memory. So we say memory, we mean just kind of a short-term storage place. And there's these terms that I want you to know. Now, this is the most important slide of this PowerPoint. I'm probably going to run out of time. I just got a couple minutes. I don't even know if I want to try this slide, but tell you what, mark this slide, and I want to come back because you got to know these terms and how to do certain calculations with these terms. And then also, I'll come to this slide, which now we're going to talk about, well, this part of the memory, this table thing. So I don't think I want to try to do it now. I'll just rush through it. We only got 2 minutes, but look over this slide, mark it, and then on Wednesday, I'll come back and pick up with this. And I want to go into some details of the terms here and then show you how that relates to this, which relates to this. Okay, so doesn't make sense now, but it will on Wednesday. Let me get off of here and go to the camera and ask, does anybody have any questions, comments, or concerns before I sign off? Nicholas. Nicholas, your hand is up.
Yes, it was. Do you hear me?
Yeah, I can hear you now, Nicholas. Hey.
Hi. Yeah, I'm on the camera now too.
I'm smiling because you know the only person that ever turns their camera on is Jacob, so I got a new face. Thank you for doing that. But go ahead.
Oh no, I did it the first day, but yeah, I haven't really done it since. Yeah, sorry about that. But anyway, I just wanted to say this morning I noticed I guess I must not have submitted the homework for last night correctly, or maybe not at all. I honestly don't remember.
Okay.
I went ahead and emailed it to you if you're willing to accept it anyway.
I think I'd rather
basically,
I'll just reset that. If you email it, I'm not gonna honest. I got like 5 different email accounts. I'm just gonna reset it later, and you can resubmit it.
okay.
I'll reset the time, and you'll be able to resubmit it.
All right. Thank you very much. I appreciate that.
Hey, send me a text, and once I've done that, I'll text you and say, hey, you can resubmit it now. Can you do that for me?
Yeah, and the text is the same number as always, right?
Yeah. Just text that number and say,
Okay.
hey, don't forget to reset that for me. That's not a problem.
All
right. Good seeing you. Anybody else?
Thanks. You too.
Thank you. Any other questions, comments? Okay. Well, you can always text me, guys, and hopefully the department gets back with me on okaying this remote thing. I don't know. We'll figure it out. And thank you for working with me on that. And I will see you guys on Wednesday. If anything comes up between now and then, please send me a text and I'll respond to it. Guys, have a great rest of the day. I'll see you on Wednesday.
You too. Thank you very much.
Thank you.